In this video, I will be discussing one of the important method of simplification of proton-coupled carbon-13 spectra, that is DEPT spectra. You know, the natural abundance of carbon-13 nuclei among the isotopes of carbon is only 1.08%. Thus, there is only a very remote chance for a carbon-13 nuclei to have another neighboring carbon-13. Thus, there is no or very remote chance for carbon-13 coupling, but the attached proton has the same spin quantum number of half as of carbon-13. Thus, there is every chance for coupling between the attached proton and the carbon-13. This carbon-13 signal split into multiplets. Also, you know, the carbon-hydrogen coupling is one bond coupling. The coupling constant for one bond coupling is very high. Thus, the difference in chemical shift and the coupling constant is very small for carbon-13 NMR. Thus, this phenomena complicates again the nature of multiplets in the carbon-13 NMR. Thus, it is necessary to simplify proton-coupled carbon-13 NMR spectra. Okay, there are three important methods for simplification of proton-coupled carbon-13 NMR. One is noise decoupling or broadband decoupling. The next one is off-resonance decoupling. And another is DEPT. Here we are discussing the last one, DEPT spectra. Okay, DEPT or Distortionless Enhancement of Polarization Transfer is a spectroscopic technique used to determine the number of hydrogen connected to each chemically equivalent sets of carbon. DEPT experiment gives a series of spectra in which carbon-13 NMR signals are transformed based on their substitution pattern. Say, for example, primary, secondary, tertiary and quaternary. Thus, from DEPT data, we can identify a quaternary carbon where there is no hydrogen attached to carbon atom, and CH where one hydrogen is attached to carbon atom, and CH2, two hydrogen attached to carbon atom, and CH3 groups where three hydrogen is directly attached to carbon atom. So we can identify whether there is any carbon or CH group or CH2 groups and CH3 groups are present in a molecule or not by using DEPT spectra. See, this is the DEPT spectra of this molecule, that is diethyl phenylamine, a tertiary amine. If we taken the normal carbon-13 spectra or broadband decoupled spectra of this molecule, it will be like this. There are 6 carbon spectra or lines. These 2 lines are of these CH3 and these CH2 groups, CH2 and CH3. Both are equivalent. See, this CH2 and this CH2 are equivalent, and this CH3 and this CH3 are equivalent. So this CH3 carbon atoms, both the CH3 carbon atoms are equivalent, and both the CH2 groups carbon atoms are equivalent. And so 2 carbon spectra, NMR spectra is obtained. The first is for CH3 group and this is for CH2 groups. And these 3 are for 3 sets of CH groups of aromatic carbon atom. It is this CH and this CH are equivalent, that is below left and below right, and this, that is this CH and this CH are equivalent, and also above this CH and this CH, left CH and the above right CH are equivalent, and this top CH is another set, and so 3 sets of CH are present in this molecule. So there are 3 carbon-13 NMR spectrum for this molecule as CH spectra. Okay, and then this line is due to this carbon atom, the quaternary carbon atom, this carbon atom. This line is for this carbon atom. So it is the normal carbon-13 broadband decoupled spectra of this diethyl phenyl amine. Then in the case of DEPT, we are using different excitation angle. For example, at 45 degree excitation angle, we will be getting CH spectra, CH2 spectra and CH3 spectra. One of the important feature of DEPT is it will not give the spectrum of or spectra for quaternary carbon atom. Here at 45 degree, we get the CH, CH2 and CH3 lines. As in the previous case, the first one is for CH3 and this second one is for CH2, and these three are for CH groups. There are three different sets of CH groups and so three different lines in 45 degree excitation angle. There is no line corresponding to this quaternary carbon atom in DEPT spectra. In 90 degree excitation angle, only CH group will be CH, the carbon-13 lines spectra of CH groups only obtained in the DEPT 90 degree excitation angle. So you will get only these three lines. The CH3 spectra and the CH2 spectra are removed from this spectra and only these three lines are obtained. These three lines are for three different sets of CH proton, that is of aromatic carbon atom. And in 135 excitation angle, we will get CH and CH3 spectra as positive lines and CH2 as negative spectra, negative or below the line, below the base. You can see here it is the line of CH2 proton. It is negative spectra, but all the other CH and CH3 are obtained as positive spectrum, but the CH2 group is obtained as negative spectrum. And by comparing these spectra, the normal carbon-13 broadband decoupled spectrum with the spectrum obtained in DEPT at 45 degree and 90 degree and 135 degree excitation angles, we can identify the compound, how many CH groups, CH2 groups and CH3 groups, and whether there is any quaternary carbon atom is present or not. Okay, the next example is this molecule. It is diethyl phthalate, diethyl phthalate. It is an ester of phthalic acid, diethyl phthalate. You can see at 0 degree, that is broadband decoupled spectrum, broadband proton decoupled spectrum of this molecule. You can see the CO group gives this signal, that is the quaternary carbon atom, and this is pertaining to this CH3 group, the first CH3 group, and this CH3 and this CH3 both are equivalent carbon atom, equivalent CH3, and so the carbon atoms are equivalent, and this CH2 and this CH2 are equivalent, and the CH2 signal is this, and there are two CH groups, equivalent CH group, one top and this bottom CH groups are equivalent, and another sets of CH2 groups, this CH2 group and these CH2 groups. So these signals are for aromatic CH groups, of aromatic carbon atoms or aromatic CH groups. Okay, then it is of broadband decoupled spectrum. Then if we examine the DEPT spectrum at 45 degree, there is no signal for this quaternary carbon atom or the CO group, but these signals are for aromatic carbon atom, and this signal for CH2 groups and this signal for CH3 groups are retained. Only the quaternary carbon atom, the signal for quaternary carbon atom is removed. And at DEPT 90 degree, that is excitation angle 90 degree, the CH groups are there. Only the CH groups, the signal of CH groups are there or retained in the DEPT 90. At 130 degree excitation angle, DEPT gives the CH signal and the CH3 signal as the positive signal, but CH2 gives the negative signal, that is below the base of the spectrum. And by comparing these spectrums, that is broadband decoupled spectrum and the DEPT at different angle, excitation angle, we can identify the molecule, whether or about how many CH3 groups and how many CH2 group, and the number of CH groups and quaternary carbon atom, and all these informations are obtained by comparing the broadband spectrum with this DEPT spectrum. Okay, yes, I conclude this discussion here. Thank you so much.